This is lecture number 3 of the course Engineering Mechanics. In the last lecture, we learnt about a frame fixed Cartesian coordinate system. Using that coordinate system, we then derived the expressions for the velocity and acceleration of a particle with respect to our frame in context. In this class, we are going to study about another type of coordinate system, which is called the cylindrical polar coordinate system. First, we will describe this coordinate system. We will describe its unit vectors. We will describe the scalar coordinates native to this coordinate system, and then we will proceed to find expressions for VPF and APF, velocity and acceleration of the same particle P and the same reference frame F, what we mentioned, what we referred to in our last lecture. It turns out that to define a cylindrical polar coordinate system, we do need a frame fixed Cartesian coordinate system in the background. Let this be the frame F. And let this be a frame fixed Cartesian coordinate system in the background. Let P be the same particle which we referred to in our last class when I was talking about a frame fixed coordinate system. In this Cartesian coordinate system, this point P had its scalar coordinates as x1, x2 and x3. However, now I want to refer to this particle and its velocity and acceleration with respect to the same frame using a cylindrical polar coordinate system. For this cylindrical polar coordinate system, the 3 unit vectors that we will have are denoted by these symbols, and the 3 scalar coordinates that will be required to reach point P are r, phi and z. In SI units, r is going to be in meters, phi is going to be in radians and z is again going to be in meters. What are the definitions of these quantities? We first drop a perpendicular from point P to the plane of x1 e1 and x2 e2. Let this perpendicular meet this plane at point P prime. Thus, point P prime is the point of intersection of perpendicular dropped from P, our particle of interest, or the location of our particle of interest, the current location of our particle of interest, to the plane x1 e1 x2 e2. Let's also join the points P prime and O. The distance or the magnitude of this vector is the first scalar coordinate of R, of our point of interest P in this coordinate system. Now note that given this definition, R is always going to be greater than or equal to 0. And also note that R is not the magnitude of RPA. It is the magnitude of, not the magnitude of RPO, but it is the magnitude of RP prime O. Mind you, RPO is here. R small r is not the magnitude of this vector, but of this vector going from O to P prime. Then we measure this angle from x1 e1 to this line segment OP prime in the direction or in the sense as shown on the diagram. So if you consider your right hand, your right palm, and if you curl all your 4 fingers towards your palm, then the direction of the thumb will be along E3. So the direction of phi is the direction of the 4 fingers of your right hand, such that the thumb points in the E3 direction. This is what the definition of phi is. Now phi is also greater than or equal to 0, and it can take values in multiples of 2 pi. It can be, once phi takes the value 2 pi, it will return to the x1 e1 axis, and then further it can take values more than 2 pi also. So this is the second coordinate here, what I mentioned. What is Z? Z is distance of P from P prime, and Z will be greater than 0 if P lies above this plane, where the word above means on this side. Z will be less than 0 if P lies below this plane. X2 E2. So this is positive Z. If P lies below here somewhere, Z can take negative value also. So Z is distance of P from P prime with this understanding that z is going to be greater than or less than 0 based on whether p is lying above or below the plane x1, e1, x2, e2. So z has this range, can go all the way from minus infinity to infinity. That can also be 0. When z is 0, indeed it will, p and p prime will coincide. It implies p and p prime coincide. Now the next question is, what are the three unit vectors, native unit vectors of our cylindrical polar coordinate systems? These are mutually perpendicular. So in that way, the cylindrical polar coordinate system is also an orthogonal coordinate system. How are these unit vectors defined? The first unit vector is defined as unit vector pointing along the vector r p prime o. In other words, er is nothing but r p prime o divided by r p prime o magnitude. This is the direction of the unit vector er. How is E phi defined? The vector unit vector E phi points in a direction perpendicular to ER and along the direction of increasing phi. In that way, the plane of ER and E phi is parallel to the plane of x1, e1 and x2, e2. So I'll draw E phi in this manner, and these two are perpendicular. So that's the second unit vector. The third unit vector of our new coordinate system is nothing but E3 itself, where E3 is the third unit vector of the frame fixed Cartesian coordinate system in the background. Ez is identical to E3. Now with R, phi, Z, ER, E phi and Ez defined, we say that define the cylindrical polar coordinate system. Now note that the cylindrical polar coordinate system, this cylindrical polar coordinate system is not a frame fixed coordinate system. Is not fixed to f, not fixed to f. Why it is not fixed to f? Is it because the origin of the coordinate system is not fixed to f, or is it because some of the unit vectors are not fixed to f? Now what is the origin of origin of our coordinate system? The origin is still z, the point O. Now O is indeed fixed in f, there is no question about it. But you observe the definition of ER and E phi. What will happen if at the next time instant point P moves from this location to say another location here? What will happen? If point P moves to this new location, you will have to drop a new perpendicular here, P prime, and then you will have to join point O to point P prime, and then this will become the new ER unit vector. This will become new E phi unit vector, and EZ unit vector will still be the same, and that will be pointing in the E3 direction. So it means that with time, as P moves with respect to f, ER and E phi unit vectors will change. It means that while trying to derive the expressions for BPF and EPF, if you come across expressions like this, you should not set that to be 0. Similarly, the second unit vector, if you come across rate of change of this quantity, this should not be set to 0. However, if you come across the rate of change of the third unit vector of the cylindrical polar coordinate system, that is still 0. The fact that there is at least one unit vector which is changing with time, and thus the fact that there is only at least one unit vector changing with time leads us to the conclusion that the cylindrical polar coordinate system is not frame fixed. We can still say that, rather it would be better to say that the cylindrical polar coordinate system is merely partially fixed, is partially fixed. Is only partially fixed to f. Okay. I want to redraw this diagram. Same current instant, the particle is here, and I drop this perpendicular, this is P prime. Mind you, it is okay to draw ER and E phi vectors with their tails fixed at origin. In the earlier diagram, I drew in this earlier diagram. Let's go back to the original position location of point P, so we don't need these things. In this diagram, I drew ER and E phi such that their tails were at point P prime. However, it doesn't matter as long as you keep the direction of this unit vector the same and translate it in a manner such that its tail goes and sits at O and the vector still points along our P prime O vector, the vector remains unchanged. Similarly, I can take this vector and translate it and take its tail and put it at O. Then if I will be pointing like this, where my cursor is, it is the same unit vector, it doesn't change. So it doesn't matter where you put the tail and head of a vector, as long as its magnitude and its direction remain the same, we are fine. So in this diagram, to make it easier to visualize things, I am putting the 3 unit vectors in this way, with all of them having their tails at point A. Now in this coordinate system, these become R, phi and Z are the scalar coordinates of point P, and this is the situation at time t as observed by this observer tied to frame F. Okay, at time t the particle is here and the person is observed. How do we write RPO? The current position vector of the particle P in this coordinate system now. That will be written as vector R prime O, RP prime O plus RP P prime, right? Go from here to here and then go to the point P. Now this can be written in the cylindrical polar coordinate system as R times a scalar, the unit vector ER plus Z times EZ, right? So it turns out the way we have defined our unit vectors in this new coordinate system, you need only 2 of the scalar coordinates to write the position vector of the current location of point P. Note that it doesn't mean phi is not important. The location of point P is indeed depending on phi also. In fact, the dependence comes through the fact that ER is pointing along P prime O direction, RP prime O, the direction of RP prime. Okay, this is the position vector. Now, as I said earlier, my real intent here is to find VPF. Now, VPF will be this. I am going to use product rule of differentiation. However, this time we should be careful because some of the unit vectors do change with respect to F. In a frame fixed Cartesian coordinate system, you can ignore the time derivative of the native unit vectors of the Cartesian coordinate system. The rate of change of unit vector E1, E2 and E3 with respect to F frame, they are 0. You can ignore them, but here some of them may be non-zero, so we will be more careful. So first I write all the terms that I will get from this derivative. Right, 4 terms I get. Now this, the rate of change of Ez is has to be the same as E3, and this is still 0. So at least we can remove this term. Let's also use the notation, simpler notation. Let's use a dot at the top of some quantities. We get this. What is this quantity? Clearly it is not 0. We discussed it earlier also. As the location of particle P changes, location of P prime will change, and thus ER will change its direction. Thus this derivative seems to be non-zero. We will have to do something about this. What exactly is this quantity? To derive the exact expression of this quantity in terms of other unit vectors or the time derivatives of the scalar coordinates of the cylindrical polar coordinate system, I am going to draw another diagram, and that diagram will be the top view of the scenario that we have here. Somebody looking from this direction on looking at the plane of x1 e1 x2 e2. So this plane is very important from the point of view of the cylindrical coordinate system. First we use this plane to define r. We also use this plane to define phi. Indeed, based on P prime and O, we defined ER. This is where ER is, and on this plane also we defined our unit vector E phi. Right, so this is the top view, such that E3 or the Ez unit vector, they are coming out of this plane. Now looking at this figure, we can write the ER unit vector as right. What am I doing? I'm trying to forcibly express ER in terms of the native unit vectors of the frame fixed Cartesian coordinate system in the background. Not only ER, I can also express E phi, the other unit vector here, as minus sine phi E1 plus cosine phi E2. It's coming from this figure. Now let's take the time derivative of this vector with respect to f. Now note that E1 and E2 are frame fixed, so we don't need to explicitly write the expressions of dE1 dt or dE2 dt with respect to f. I can directly write this as right, and on this side I will have this. Now once you have this expression, we realize that this is nothing but phi dot of E phi. And on this side, I missed something here. I meant to write d E phi dt of f. So E phi is this, of course, rate of change of this unit vector is this. And then we realize that this is nothing but minus phi dot ER. So by mere visualization, we were expecting that the rate of change of ER with respect to f will be non-zero, and also the rate of change of E phi with respect to frame f will be non-zero. Now we have the exact expressions of these rates of change in the two unit vectors. Let me label them as point number 3 and point number 4. Now with these expressions in hand, I go back here and express VPF in its most simple form as this becomes so this is the expression, most simplified expression of the velocity of the particle p with respect to f using the cylindrical polar coordinate system. Let's call it 5. Once we have VPF, we are now ready to find APF also. APF is going to be the rate of change of VPF with respect to f. With respect to f, we have 3 terms inside the derivative. If you apply product rule of differentiation, we are going to get 6 such terms, and I'm going to write them explicitly first. I will get actually it's going to be more than 6 because here it's a product of 3 terms. So the product rule of differentiation will give us three terms here. So this is the first term, this is the second term, and then I have the third term coming out of it. And then this will give us two terms, right? These two terms have come from this. Fine. This is going to be 0, we know. And this we derived just a few minutes ago. This is going to be phi times E phi, phi dot times E phi. And this also I derived here on the right hand side. Rate of change of E phi with respect to F is minus phi dot ER. Now using these expressions here and collecting the coefficients of ER, E phi and EZ, we can get the final expression of APF. Let's do this exercise. Everything is there on the screen now. So ER gets first contribution as R double dot, it's taken care of. Where else we have ER? We have ER here, so we get R phi dot square, this is taken care of. E phi, I get one contribution from here, another from here, and both are having the same scalar part, R dot phi dot and R dot phi dot. Going to put 2 here. I have another contribution to E phi coming as R phi double dot, and this is also taken care of. Left only with one component here, which is Z double. So this is the final expression in the most simplified form for the acceleration of particle P with respect to F when I use the cylindrical polar coordinate system as my working coordinate system.